Krishna, and hi everybody. Yeah, let me start. My name is Alan Cantle, and I'm the HPC subproject technical lead. The HPC project has been running for a while in OCP, but it's had a couple of misstarts, and I'm actually helping to reboot it over the last few months now. And today I'm going to give you a quick update, a look at what we're trying to cover. And I'm joined with several colleagues from HPE, IBM, Penguin Computing, Intel, and NVIDIA, who will be giving lightning talks from their perspective of what they would love to see from OCP on HPC going forward. So the scope exploration we're looking at is OCP project efforts. If we look at what's going on in OCP, they're increasingly looking HPC-like. Okay, typically they're dealing with high performance data analytics or machine learning, whereas traditional HPC is more physics challenges. But infrastructure-wise, architecture-wise, they do look very similar. HPC is traditionally low volume, expensive in custom machines, whereas the hyperscalers are massive scale, very cost-sensitive machines. So maybe, what can OCP learn and leverage from the HPC industry? And what can, can OCP actually help bring low-cost HPC to the masses? And that's my vision and hope. So we're going to hear from the experts, as I said, and see their perspective on what they think we can do to help them. But first, let me just give a quick overview. The #1 supercomputer in the world is the Fujitsu FX100. It's a 415 petaflop machine. We don't know, I couldn't find the power numbers, but it's a whopping $1.2 billion machine. It is very modular, 2 nodes in a small liquid cooled card. They are plugged into 24 in a main unit and then 8 main units in a rack. And it can be configured up to 1.3 exaflops. And it's in a classic 16 mesh torus topology, as you can see on the left. The computer before that, for a couple of years, was the Summit HPC from IBM and NVIDIA. And that was a heterogeneous machine with 200 petaflops and cost $300 million. And I think this one is an interesting architecture. It's got very high bandwidth from the processors to the accelerator modules, and it's very applicable to what we're looking at. We've been discussing, actually, obviously, we're looking at not only the data center, but the edge. And so should we be looking at edge HPC or data center HPC? So I've shown a couple of examples on the left. We've got the Tesla AI self-driving processor with its liquid cooling, all very, very custom, and a traditional backplane embedded computer from the military world. Just for posterity and just to show, the good old Cray 1, all that massive wiring in the plug-in cards there in terms of the modularity of that one. Should we be focusing on one of these two, or maybe we should focus on both? But if we come back to OCP, what have we been up to in OCP, and what examples could we potentially leverage in HPC? So we've got the OCP server side and the OCP OAI infrastructure with the universal baseboard and the accelerator modules. And this one in particular is quite interesting. It looks very much like it's inspired by the NVIDIA SXM modules, but it's heterogeneous. It can take a multitude of different accelerators. And so, and then the OCP NIC 3.0 is a plug-in card, which could look like maybe more for embedded use cases as well as just this NIC. So we have some building blocks here that we potentially could leverage in our HPC efforts. Just to look at the Summit HPC and say, could we build that from the OCP pieces? Well, we could. We could take an OCP server, an OAI chassis, and put them together. Just as a quick comparison, the performance density would be half of the Summit node, 4U versus 2U. The host accelerator to the host to accelerator is only PCIe, so you have very limited bandwidth and latency impacts on that one. But the OAM does have 8 accelerators, Summit has 6, and it's heterogeneous accelerators, so you have more flexibility there. So this is an interesting one. And if I pull on this thread a little bit more, while I was working with Molex before I left, But basically, we were looking at how do we enable the OAI platform to be upgraded to the 112 gig speeds and actually support coherent links to host processors. So here's a model of just a bare bones model of the cabling, the bypass cabling that we added. So basically we have the direct coherent interconnect. So we're replacing the connection to the host interface board with a cable to a lower board, so we could connect OpenCAPI, CXL, or Infinity Fabric and bypass the PCI bus. Then we have an ability to cable, blind mate cable attach directly to the OEM module. We still keep the standard MES connectors, so hopefully this would be forward compatible and backward compatible, but we could support 112 gig. With that interconnect, we could then support the corner-to-corner communications at 112 gig. We found out that you couldn't do 112 gig and keep within the 30 dB budget across the corner-to-corner modules. So this would be a way of getting the 112 gig there. And finally, we could do fabric expansion out of the chassis to 112 gig with retimerless. The current system has retimers, but this would be a retimerless connection between chassis for expansion of accelerator modules. So this is just one example of what could potentially be done if we were to take what OCP has done and then upgrade it for HPC. Evolutionary approach, we're leveraging a lot from what all the efforts that have been done. Maybe we need to take more revolutionary steps as well, but I think that's what our work group needs to discuss. So this was just really an example, a courtesy of Molex. So thanks for Molex for sharing this information. It obviously has their interconnect, but there's other bypass options from other vendors as well. On Edge or HPC, if we look at that, we've got the plug-in card from the military world. I'm not sure if we could upgrade the NIC and the EDSFF standard to be more ruggedized and more suited for some of the embedded applications. And equally, the Tesla module there, arguably, there's a chance that maybe we could leverage the OEM modules with the liquid cooling for some embedded HPC applications. So these are just a couple of ideas. We've had a few membership discussions so far, about 3 so far, and some of the topic areas that are coming through are infrastructure friendly to HPC, including support for continuous integration and continuous deployment. So the big infrastructure, so we can feed these machines, these very high performance machines, will be critical. Standardize the HPC management and telemetry with OpenBMC seems to be a thread that's coming through. So that's an interesting one. Apparently, all these supercomputers tend to have different management software and firmware levels. And then there's the flexibility and modularity, which is at the core of OCP, obviously. But we need to focus on the ever-increasing performance density, which is a relentless march, especially from all the silicon vendors, and we need to continue to support them. And finally, the interconnect performance, scalability and compatibility are key issues, especially with a heterogeneous system. So how do we normalize those as well, or allow multiple ones in BF to be switchable? Oops, sorry. So my call to action is please stay and listen to the experts' views. I'm by no means an expert in this area, and if you like what you see and you'd like to help us define a way of democratizing HPC and opening it up for others and getting the cost basis down, then please come and join us in my sub project. And with that, I'll hand over to the next presentation, which was from